Okay, welcome to the next lecture on software design. We're going to pick up where we left off. We were talking about various kinds of software architectures, and we first reviewed some of the architectures that you're already familiar with, such as the client-server architecture, and let's just go back and look at these slides for a second here. We looked at the client-server architecture, the multi-layer architecture. Okay, so those are architectures that we've looked at and reviewed several times. Then we looked at the broker architecture, which is where you take some kind of a distributed object whose job is to route messages to some other distributed object, some other server somewhere, so that allows you to move the servers around. The typical concept here is that you've got remote objects on different servers, and the broker can decide where to route these messages to. Then we talked about the transaction processing architecture, which is one of the earlier architectures in software engineering. It's been around since the early days of computing, where traditionally you had a program that would do nothing but read in records, process them, and output revised records, perhaps to several different files. But one of the things it had to do when it read in records was to determine what transaction to perform on them. And so it would then call a different procedure depending on what transaction was required. And so we have this notion of the transaction dispatcher. What we're going to look at today is the remaining architectural patterns, starting with the pipe and filter architecture. So the pipe and filter architecture involves a series of units, which we're going to call filters, each of which takes an input in a certain data format and outputs it in a related, similar data format. The concept is that you can plug these filters in a chain, a pipeline of some kind, and perform all kinds of different functions depending on how you configure the set of filters. Okay? So we have a stream of data in a simple format. This might be a stream corresponding to sound. It might be just some kind of simple string data. No matter what the format is, it's a simple format that we're going to pass through a pipeline of filters to do some kind of transformation, some kind of selection on that data. And we'll see an example in a minute. The concept is that data is a series of data is fed into the pipeline, to be constantly fed into the pipeline, and the processes conceptually at least work concurrently. So we've got a number of things, and each stage in the pipeline is working on the next piece of data, and the previous stage in the pipeline is working on the previous piece of data. Let's take a look at an example. This example on slide 80 shows a whole bunch of boxes. Each of these boxes is a component, okay, using the notion of the component from the component diagram we looked at last day. And each of these boxes then does something to sound. We see at the very beginning microphones. Okay, we're showing a stereo kind of sound input here, so we have two microphones. And so we're passing down through this network stereo sound encoded in some sound encoding format. The first stage is the encoder. Okay, so it is taking the input, digital or analog input from the microphones and encoding it. That's the input to the pipeline. Then we have a unit called cancel audio. This unit is involved in changing in some way this sound. Okay, so it's filter. This is a filter unit. It's changing the sound in some way, and it says here it's canceling echo. So presumably it's imposing some kind of delay, and then looking to see if a similar waveform is coming after a certain amount of delay behind it. But it's outputting sound again. So it's inputting sound and outputting sound. That's the key thing. It's done some kind of transformation, some kind of filtering, but it's still outputting sound. Then we have cancel noise. Now cancel noise is actually taking two inputs, both of which are sound. You'll notice that there is an encoder for ambient noise. So that's maybe taking some sound input from maybe the back of the room and feeding that into the cancel noise. The cancel echo is feeding into the cancel noise. The two of them together are then working to filter the sound from the original microphones and an outputting sound that has less of the noise, less of what was heard in the back and more of what was heard in the front. This is also a filter. It's a classical filter in the sense that it takes two inputs and creates one output, but it still is perfectly legitimate in the pipe and filter architecture. So you can have various kinds of branches and joins in the pipe and filter architecture. We move on, remove non-voice frequencies, equalize dynamic range. Those are all things that are changing certain aspects of the sound. Notice that all of these things, or many of these things, can be reusable. In fact, maybe I could even change the order of these two things, or take one of them out, and it would still work. I could take out the cancel noise. The system would still work. Take out the cancel echo. The system would still work. I would have different qualities as a result. So each of these is a reusable component that takes a standard form of input, produces a standard form of output, typically the same form, although it doesn't have to be, and then passes it on to the next one. Compress is an example of a filter which takes the form of input and doesn't produce the same output. Okay, so it's compressing and producing a compressed output. Transmit and receive are taking input and sending it over a network and receiving it over the network, and then decompress does the obvious thing. Notice that we could just pipe equalize dynamic range right into encode speaker output if we wanted to, and avoid this compression, transmission, receiving, and decompressing. And we could also not compress at all if we didn't want to. And then finally we have the encode speaker output that sends the output out. Okay? So this is a classic example of a pipe and filter system. But you can have pipe and filter systems in many kinds of environments. You can have them, they're very common in the Unix environment where you're processing typically string data, so you might have a sort process that sorts, you might have a process that removes duplicates, you might have a process that selects a subset of records, a process that computes some values based on numbers in the records and adds an extra item to the end of each record and then outputs the result. Okay, I often do that kind of thing when I want to analyze large volumes of data that are stored in files, for example. Okay? You could do that on databases as well. I can have a series of filters that start by reading the database and then doing various processes on each record as they go through, and then finally producing some kind of report in the end. Okay, the classic non-pipe and filter architecture would do that in one single unit, whereas a pipe and filter system would divide these things up into smaller components and do each of those pieces of work as a step at a time. Okay? Any questions about the pipe and filter architecture then? Okay, so just flipping back to slide 79 for a second, we say that the architecture is a very flexible one. It's one of the more flexible ones that we've seen so far. Almost all the components can be removed. Okay, we can shuffle them around. We can replace components quite readily by other components that maybe perform similar but slightly different functions, maybe cancelling noise with a slightly different algorithm. We can insert new components that we come up with relatively easily without hardly any programming, right? Very little programming would be involved in simply inserting a new component in. So very flexible, very powerful. And we can reorder components as well in some cases. We can say, well, we'll put this one first and that one second. Slightly different results in the end. You'll notice that most of these components, because they take a standard input and produce a standard output without any side effects, can be called functionally cohesive. Okay, so we have examples of typical functionally cohesive components here. Any more questions? Okay, and again, as with all of these architectural patterns or styles, we have a number of advantages and disadvantages, and I won't go into all of them in detail, but just for example, it says on point 2 that the processors have functional cohesion, so that's how they improve cohesion. The coupling is very low because they only have one input and one output, so they're only coupled to their neighbors, and they're not really strongly coupled to those because their neighbors could be anything. They don't need to know what their neighbors are. They just need to know the output they produce. So the coupling is almost non-existent here. That's very, very strong adherence to these software engineering principles. Clearly there's strong divide and conquer. There's strong abstraction, strong reusability, potentially strong reuse, very flexible, very testable too, because we can just test each of these components independently. And we can design defensively. We have very nice interfaces to these things to make sure that they don't accept any invalid data, okay, on input. So almost all of the software engineering principles are very strongly supported by the pipe and filter architecture. It's highly recommended. If you can put a piece of pipe and filter into a system, it certainly buys you a lot of flexibility. Okay, let's move on then to another one of these patterns, Model View Controller. Model View Controller is a pattern that was invented in around about the 1980s, early 1980s, for graphical user interface use. It was made famous in the context of the Smalltalk programming language and is, in one form or another, still present in Java and similar languages. It was the original architectural pattern in which people realized that you need to separate the functional core of the system from the view of the system, from the user interface layer of the system. So in some sense it's strongly related to the layered architecture, but it makes an extra division in the layer, in the user interface layer that we'll see in a second. So we have three major types of components. The model is what in the MVC architecture is called, is the name for the functional part of the system. Okay, it's the part of the system that contains the data that we're manipulating in this system. The view is what is displayed on the screen. Okay, so that's clear enough. It's displaying the windows, it's displaying the dialog boxes and the text boxes, scroll bars, things like that. And then there's the controller, which is the other part of the user interface. The controller is what accepts user input and decides what to do with the user input. Okay, so we've separated the UI into into two parts, the system into three parts. Whereas the type of UI I talked about before was really only a split of the system into two parts. So we're separating the decisions about what to display on the screen from the decisions about what to do when we get user input from mouse clicks and typing and things like that. That's the model view controller pattern, and it uses the observer pattern internally, the observer design pattern, to manage some of the work, in particular making sure that the model and the view are separated from each other. So slide 84 has a diagram of the various pieces of this pattern. So we see the model, we see the view, we see the controller. The model, then, we understand what that is. It notifies the view about changes. Okay, so this is where we use the observer pattern. The model is an observable. The view is an observer. The view will update itself whenever the model says, I've changed. That's the way that works. The controller, it will be creating and updating the view as well. The controller will create the initial view, just put the initial pieces of the view on the screen typically. Okay, because remember, generally the user interface is what controls the system. The system starts up, the user interface starts up, and initiates the functional layer. That's the way it works in SimpleChat. Okay, you've got your main program, which is part of the user interface, and it decides that it will start up the functional part of the system. And from that point on, the functional part of the system runs on its own. So here, when the user interface starts up, it creates, or the controller part creates the view on the screen, and occasionally will update that. So sometimes if the user clicks on something saying, show me a new window, the controller will, in fact, display a new piece of the window without going to the model. The model is only the underlying data. Okay, the user interface can sometimes respond to various commands without needing to do anything with the underlying model. Okay, that's an important thing to remember. So the controller will both create and sometimes update the view. Okay, the controller receives the events from the actor, from the end user. So the end user is clicking on things, is typing data. Some of those clicks, some of those things which the end user does in the controller are interpreted as things that need to change the UI. Okay, so messages are sent to the view to update it. Other things are interpreted as changes or commands that need to be sent down to the model. And so we have a channel from the controller to the model called modify. So there will be requests to modify, or requests to queries, perhaps, would also be included in that. Okay, and then the model will then say, I've changed, here's my response. And that response will end up being displayed in the view. Okay, so we have these three main channels. There are some other channels too. that occur, but in general, this is the simplified model of the model view controller architecture. And the key concept is separating view from controller. People say, well, I should be able to replace my visual aspect with some other visual way of looking at the system without necessarily changing in detail how the controller works. I want the user's responses to be the same, but maybe I have a fancier looking set of widgets for actually doing the display. So I can change my widgets on display so they look nicer, so they've got different fonts, so they've got different style, maybe, but leave the controller alone. Alternatively, I can leave those windows the same and change the controller. I might decide to change the controller so it responds differently to certain kinds of user input. And so people who invented MVC said we can separate concerns there, in addition to separating concerns with the model. Not every architecture does this. You'll notice that in Java you've got things like action listeners and those kinds of things that act in the role of controller. The main program that sets up the UI acts in the role of controller as well. Okay? And the view are the things like your frames and things like that. So there are different classes, but we typically don't model these as two completely separate components. We tend to group together the two as a UI. But the classic MVC architecture separates them. Any questions about this? Yeah?
Does they create an update and notify what changes work in parallel?
Yeah, well, if you imagine conceptually all of these running independently, I mean in a concurrent fashion, they aren't actually running concurrently because they're typically on one machine, but if you imagine them running concurrently, then the user can click on the controller at any point in time, okay? The view has got to keep itself updated at all times, and the model conceptually could be a concurrent thing. So conceptually they could be concurrent, but in actual practice, the controller is in control. And so the user clicks, it sends a modify message or a query message to the model. The model does some calculations very fast, and then notifies its observers that it's got responses or it's got changes to reflect on the screen, and that notifier goes up to the view, which then changes the response. Okay, so there is a flow in the direction of the arrows here, but it could be concurrent if you wanted to do it that way. Good question. Any other questions? Okay. So again, there are some pros and cons of the MVC architecture. I'm not going to go into them in detail, but you can take a look at these as well, on your own time. Okay, so that brings us to the end of the list of architectures that I want you to be familiar with. There are many others. This is an overview of the key ones that you will typically want to think about when you're doing basic designs. Okay, so all the ones we've talked about are very basic architectures that can be put together in different ways to create a more complex architecture. You can have pieces of your system that are layered. You can use the MVC for the UI aspect of your system. You can use the pipe and filter architecture for certain computations that you're doing. Okay, you can mix and match these things. You can use the broker architecture for accessing information on remote servers where you want to be able to move the remote server around. Okay, so you can mix all these together in different parts of your system to create a larger system that has quite a complex architecture. I want to say a few words about writing a good design document. We've talked about writing a good requirements document back in Chapter 4. Many of those guidelines will apply to writing a good design document in the sense that we can have layers of hierarchies of design documents. We need to carefully review the design document. It is important to write down aspects of your design. You don't have to write a tome of hundreds and hundreds of pages of your design in every system. Occasionally, if you're designing a system for a nuclear power plant or a very, very large system, you will have a very, very thick design document. But some design documents can be much thinner than that. Nevertheless, it's a good idea to do it. Okay? It's a good idea to write down your key decisions so that you can communicate them to implementers, so that you remember them yourself, so that maintainers can look at those, but also because it helps you to think. The process of writing things down helps you to think. Whether it be just writing down the architecture, sketching the architecture, drawing a few pictures, it will be better to help you think that way than just jumping right into the code. Okay? So you should write things down. We should consider all documents to be a means of communication. Okay? You're not just documenting for documenting's sake. You have to think of communication. Who's your audience? As I said, those who will be implementing, those who are modifying, and also those who are interfacing to your system. Maybe other people creating alternative ways of accessing parts of your design. Okay? All of these are potential members of the audience for your system. So you have to think about, well, if my audience is modifying the system, what will they want to know? They might want to know places where we've built in flexibility, where we've built in hooks, that people can add functionality later on, or where we explicitly left something open so that people can easily add a new feature on later on. Okay, that's the kind of thing that the maintainers are interested in, as well as how does it work. On slide 87, I'm showing a suggested set of headings. You don't have to put all these headings in your document. Just like in the requirements document, I suggested a set of headings. I'm suggesting that you have a purpose for the document so people understand what it's describing, the aspect of the system. The priorities, we talked about priorities that we applied last lecture. So for example, if security is your top priority, you want to put that in your document so people understand why you made the decision. Okay, if you don't actually write down things like we put security as a top priority, then people might wonder why you had made certain decisions. But if you say that, they'll understand better. If you say efficiency was my top priority, they'll understand then why you maybe sacrificed certain other qualities like coupling and cohesion. Because you are after efficiency, that sometimes means that you have to sacrifice other qualities. And they won't understand your decisions unless you state what those priorities are. Outline, issues, and other details. This issues thing is the structure that I showed you in the requirements, okay, where you say, what are the things that we spent time thinking about? You don't have to document every single decision. You might, for example, not every single time document why you used client-server versus a monolithic system, why you used Java versus C++. You might just say, well, it's a small enough system, we're not going to write that down. It's just simply everybody in this organization does things using Java, so that's enough. But you're going to document decisions where you had to put considerable thought into the pros and cons. And you just want to write down what those pros and cons were, how you did the weighting. Maybe you, in fact, include any mathematical or cost-benefit calculations there so people can see why you made the decision, and then what your final decision was. Okay? It's not really enough in your design document to just document what the thing is. You need to give rationale. Rationale makes people understand. Okay? If you just say what you did, well, you know, that goes over their head. But if you say why you did it, that allows people to think the way you thought. And that's much more powerful. So when you're doing a design document, there are some things you can leave out. One of the key things to leave out is things that will be readily obvious. Okay? So you don't need to say, in this system we have the following procedures. 1, 2, 3, 4, 5. We have the following 10 classes. Okay? With the following methods. Well, you don't need to do that because you can generate that information from using JavaDoc. You don't need to write that down. In fact, if you want to generate a system that has 10 classes and a whole bunch of methods, what I suggest you do is you start by just sketching out the code. For here's the class definition, here's methods which are empty with empty bodies. And then click on JavaDoc, generate the JavaDoc, and out comes your design. Bang. Right? There's no point writing it all down first and then doing that step of sketching out the code. That flies in the face of what some people would say in software engineering, don't jump into code. I'm not saying do all the coding. I'm just saying use the structure of your end code as a way of doing the design, which then leads to automatic documentation. Okay. Also, don't put stuff in the design document that could be easily put in the comments of the code. So if, for example, you want to design an algorithm, well, the way I go about designing algorithms is I write pseudocode that looks like the comments, and I put step 1, do this, step 2, do that, step 3, do that, and that just goes right in the comments of the code anyway. And later on, I'll fill the real code in. And that's a way that I like to document my algorithms, okay, rather than writing them out in detail in a separate design document. Occasionally, you might need to. If you wanted to do mathematical formulas or some other kind of detailed mathematical work that can only really be expressed in a document that supports that kind of typography, then you will need a separate design document. But if you can put the information clearly enough in the code as comments, write those comments first, and then later on, when you get into implementation, fill in the details. All right? So just do some logical thinking about what's really going to be useful in the design document and what's not going to be useful there. A lot of project managers, a lot of organizations don't think quite as clearly about this as I think they need to. And the source code itself is, in actual fact, a form of documentation. It's the ultimate detailed form of documentation. But a lot of the things in that, like the overall structure and the comments, can be considered quite high-level documentation. Any questions or comments about that? So the next few slides show design of a feature of SimpleChat. I'll just go briefly over some of these things. This is the blocking feature. You've all done a design of other features of the system, and you've seen the requirements of this feature earlier on. The purpose of this, therefore, is to describe important aspects of the design of features that implement certain commands in SimpleChat. So I'm listing those. Under the priorities section, I'm saying that, well, here are the priorities that we're using. Priority number 1 is maintainability here. I want to focus on flexibility, maintainability. Usability is a second priority, although usability is something that hopefully we've taken care of already in the requirements. But if there are usability issues still left, it's still a high priority. Portability is important. That just means, stay in Java and don't do things that would step out of those bounds. Efficiency is the lowest priority here. We're not going to focus on efficiency in this particular system. Maybe the assumption is that the amount of data, the amount of computations involved are so low that efficiency will never rear its head as an issue. So let's not worry about efficiency and explicitly put it last, because otherwise people tend to think too much about efficiency too early. One of the strategies for dealing with efficiency is design with efficiency as lowest priority, measure the performance of your system according to the requirements, and if the performance is adequate, you're done. If the performance is not adequate, then optimize relevant parts of the system. Find out where the system is using the most resources and try and optimize those parts. That is a recommended approach to design that sometimes works. Doesn't always work, because sometimes you have to consider efficiency from day one, but it certainly would be worth thinking about to consider efficiency as a little bit behind the other priorities in many cases. So then we have the outline of the design. It just says that very simply in one paragraph. It's one feature, right? We're implementing a blocking feature, so this is going to be a short document. It says blocking information will be monitored in the connection to client objects, and the commands will update and query data using set value and get value. Many of the features that you can add to SimpleChat will be done this way. Many of the features that you're implementing will simply be done using exactly this outline. Simply setting in values in connection to client, getting values, and with a few changes to the response to commands in handle message from client. Okay. But relatively few of those. And then there's some issues. These look exactly like the issues in the requirements document. Issue 1, where should we store information regarding the establishment of blocking? Okay, well, we already said that we're going to do it in connection to client, but is it going to be in the connection to client associated with the client requesting the block, or in the connection to client associated with the blocked client? Could be in either. And what are the pros and cons? How do we work this thing out? Well, it turns out that we have to consider this as two possibilities, but the only one that really makes sense is that it be in the associated with the with one of these. Let's read what it says here. Decision says 2.2 of the specification. So we're referring back to the requirements. Says that we'd be able to block a client even if that client is not logged on. Okay, so somebody logs back on again, they're still blocked. Otherwise, it gives you a quick way of cheating by just logging off and logging back on again, and then you're not blocked anymore. So we must choose option 1.1. Okay, first option here. Since otherwise we will lose the connection to client when clients log off. So it's the client that's requesting the block that has to store the information corresponding to the blocking. So if I request a block from you, I don't want you sending messages to me, I have to put this thing in my connection to client information on the server end so that when you send in messages to me, those messages don't get through to me. So I'm requesting the block. I don't put it on your end. I could put it on your end and so that it tags it and says don't send messages to Tim, but that won't work because you can log off and log back on again and that information's gone. Okay? So that's the design decision that we've made here. And then we move on to some details which describe exactly what commands will be put in there and what other messages will be done. On the client side, there's not very much except adding a few commands. On the server side, we have to make a change to handle message from client, and it describes roughly what these things are going to do. Okay, and I won't go into those in detail, but I'll let you look at those yourselves to understand that. Hopefully, because you're working on forwarding, you've already looked at this stuff and you already understand how these things work. If you haven't looked at it, well, now's the time, because you only have a little bit more time to work on this project. Okay. Any questions about some of these design issues we've talked about? Okay, let's wrap up then by just quickly surveying difficulties and risks. Design takes experience. Generally speaking, you will consider yourself an expert designer after a number of years, 2-3 years, working in a system, working in the industry as a whole, and doing plenty of design. So it's not something that you can do right away. And so if you're plunked into a large system, you should work with other software engineers. You can probably design small systems yourself more or less right away, or more or less after you've finished your degree program. But wait until you've had a considerable experience in design before you actually go out and try and design large systems. Because otherwise you're going to end up with bad design. A lot of systems out there are badly designed because they were designed by people who didn't really understand the underlying principles of software design, or were new hires and so on, things like that. So design is something which sets the whole tone for a system, especially the architecture part. And some people say that architecture should be the more senior designers who've had a lot of seasoned experience with alternatives, the more so for the larger the system. And poor designs lead to high maintenance. We know that software has far higher maintenance than it should. Okay. So if we can only have more experienced designers working on the designs earlier on, we'll end up with lower costs in maintenance later on. And you have to constantly pay attention to design. As you're working through the maintenance of a system, adding new features, changing it, you have to be aware of the original design, you have to be aware of how the design is evolving, and keep the quality of the design high. Sometimes you might need to make major changes to the design to make sure that that flexibility remains there. That can be a challenge at times. Okay. So careful management of the change of the design is important. All right, well, that brings us to the end of Chapter 9. And we'll now move on to Chapter 10. Okay, so we've talked about a lot of issues to do with requirements in Chapter 4 and then design and modeling. What happens when you have an actual system? Well, you have to test it. We talked a little bit about testing user interfaces in the user interface chapter. Now we're going to talk about some strategies and techniques for testing systems as a whole from a more technical perspective. Testing and inspecting to ensure high quality. In fact, this chapter is more than just testing. There is also some material on quality in general in this chapter, which we'll look at. It turns out that for undergraduates, testing is probably the biggest thing you need to learn regarding quality. However, among seasoned software engineers who've been out there working in industry for a long time, there are many, many other areas of quality that they will spend equal, if not more, time on than testing. Different aspects of quality assurance, auditing, quality standards, quality processes. There's many, many issues to do with quality. But at an undergraduate level, we focus you on testing because we think that that's where you'll learn more and what you'll be able to take into industry right away. So let's start off with some basic definitions. And it's important to understand these definitions clearly, because not understanding the way these things are defined means that you won't understand some of the things we're talking about when we talk about testing in general and quality. I want to distinguish between failures, defects, and errors. Okay? A failure is an occurrence of something going wrong. Okay? It might be a crash, but it doesn't have to be a crash. It could be invalid data appearing on the screen. It could be invalid data being saved or transmitted over the network. It could be the system going to the wrong place when you navigate. It could be something not appearing on the screen when you expected it to. Okay? It could be even, as we'll see later on, a problem in the documentation where a user goes to read documentation and gets confused. That's a failure of the documentation to give them the information that they were expecting to get. Especially that will be true in online help, where it's part of the system and you ask a question, it doesn't give you the help you want. Okay, so all of these represent different types of failures, with crashes being very bad and crashes that cause devastation being the worst. Okay? But they're all failures of one kind or another. We can measure the frequency of failures. This is the reliability. The reliability isn't the number of defects or bugs. The reliability is measured in terms of the failures, because let's say there's only one bug in the system and it causes a crash. Okay? Well, if that crash only occurred once a year, that wouldn't be so bad. If it occurs every 5 minutes, that's a lot worse, even though it's caused by just the one bug. So there might be a huge system with one bug, but it's a lot worse if failures are occurring more frequently. So we measure reliability in terms of failures, okay? Not the defects or bugs that we'll talk about next. And so one of the objectives of design is to achieve reliability, and that means low failure rate. It's one of the things we want to try and achieve. And a failure is often considered to result from violation of a requirement. Okay, so if any of the requirements is not adhered to, that's a failure. And some of these requirements are implicit. Like, the requirements very rarely say, this system shall not crash. Okay, that's just an implicit requirement. We know the system shouldn't crash. Okay, so, still a violation of requirements, though. It just doesn't say it in outright words. But if the system said, if I block messages from Joe, then Joe's messages will not reach me, and a message from Joe does reach me, that is an explicit violation of a requirement. It's a failure because a message reached me that shouldn't have reached me. Violation of requirements. Violation of requirements can be for non-functional requirements and functional requirements. The non-functional ones would be, for example, response time. Okay, if I type a command and it takes me 10 seconds to get a response, and the requirement said that all responses should be within 2 seconds, that is a failure. Okay. The system may still work slower than expected. We still consider it a failure if the requirements are not adhered to. Okay. So don't think of failure equal to crash. Failure is a violation of any requirement. A defect, then, often called a bug, is the underlying thing in the code, in the design, that is leading to failures. Okay, some kind of flaw somehow in the system. It could be a line of code that's wrong, or it could be some whole piece of the design that is not designed efficiently enough. Okay? Whatever it is, it's a defect in the design or the code, and sometimes several defects together work together to give rise to a failure. So you might have a crash that would not normally occur. There's a bug in the code that maybe some value is allowed to be entered which shouldn't be allowed. Maybe I enter months and I can enter the 31st of April, and the system perfectly happily accepts 31st of April. Well, that's a defect. It shouldn't allow me to enter 31st of April because there's only 30 days in April. But it doesn't cause a crash and nothing happens in the system. But what would be another another defect would be if that 31st of April then resulted in causing some calculations to be messed up, which resulted in the system crashing. Okay, let's say did some calculations that made no sense and ended up taking the square root of a negative number, for example. Okay, and then you have a crash, and that crash is the result of a whole sequence of defects that all work together to give rise to an invalid value that causes the crash. Okay, and sometimes multiple different types of failures can be caused by the same bug. Okay, so if I have one defect that is allowing invalid data into the system, the fact that invalid data is in the system is one thing, and then that might start showing up as different kinds of failures. Sometimes it crashes, sometimes it gives the wrong results, sometimes it works too slowly. Various kinds of things can occur over time, many different manifestations, many different types of failures, all caused by one bug, one defect. And then finally there's this term error. The word error has a number of meanings in software engineering, but one meaning of the word error is a mistake made by a software engineer. So as a human being, I'm doing a design or I'm coding the system, I make an error, typographical error maybe, that leads to a defect in the code which isn't detected, which leads to a failure. Okay? So just a notion of error. We'll see another notion of error later on, but a notion of error is something made by an active agent, in this case the human programmer. Later on we'll talk about errors of numerical calculation made by the computation itself. So a defect is something static, an error is something active. That's the way I like to look at it. When we're talking about testing, or any kind of quality assurance, we need to think in terms of efficiency and effectiveness. Okay, effectiveness means, are we finding all the defects and reducing the potential for failures? Efficiency means, are we doing it with fewest possible resources? Are we taking the least time of all the testers? We don't want our testers to spend hundreds and thousands of hours testing. We prefer if they can do the same quality job in a few hours, far more efficient. Okay? So we want to try and focus on achieving, in parallel, both effectiveness and efficiency. Testing is a job that's like detective work. Now, we're not talking about debugging here. Debugging is like detective work too. But testing is like detective work because what your job is to try and figure out bugs that might be present. It's like going out and saying, well, we don't know if any crimes are out there, but we're going to be in preventive. It's like preventive detective work, you know, security monitoring. You know, we want to make sure that there's no crooks actually breaking into our system. So we're going to be monitoring. We're going to be guessing how the crooks might break in, seeing if they're doing it. Okay. So one of the things you have to do as a good tester is to understand how programmers and designers work. What kind of thought processes do designers use, and therefore what kind of mistakes might they make? Same thing with programmers. Okay? How do they think? What kind of mistakes might they have injected into the system? You don't leave anything uncovered. You try and uncover all the possible places where there could be latent defects or latent bugs. You have to be suspicious. Okay? So you need to be meticulous when you're doing this kind of work effectively. And you have to do that without taking excessive amount of time. Overall strategies for testing. The first strategy is black box testing. Black box testing says we're going to take a component or take a system and we're going to test it as a chunk by putting its inputs in and seeing what the outputs are, and seeing if those outputs are what we expect. If they're not what we expect, that's a failure, and we have to then go in and track down the internal defect that caused the failure. Okay, so in testing, we're detecting failures, which will then have to be investigated to find the defect. Okay? Black box testing, we don't, as we're testing, look inside the system. We can't see the source code. We can't see the data that's internal. All we can see are the inputs that we provide and the outputs that come out. whether they be data, whether they be sound, whether they be visual appearance on the screen. That's all we can see, that's all we can work with. We also can't look at the design documents. We have access to the requirements because we're testing against the requirements. We say, okay, here's the requirements here. We're going to test to see if this requirement is fulfilled. We write what's called a test case, we'll see in a minute. And then we provide input to the system and see if the output corresponds to what those requirements said. So we see the requirements document, but we don't see the design document. Then we have a second kind of testing, also called white box testing or structural testing. This is the kind of testing where, as a tester, you do get to see the inside of a system. I can actually take a look at my executing lines of code. I can put probes in there to see what the data values are, whether it be print statements or whether it be running it through a debugger. Okay? And this allows me to make sure that the flow of all the if statements and the while loops and the data setting and getting values are all what I would reasonably expect. With white box or glass box testing, I'm actually seeing inside the design in detail. It's quite a different thing to do, quite a different aspect of testing. You don't always do it. Black box testing is always done. Okay, this second form of testing is done only in situations where you need to really focus on high quality, or if you're the designer. Quite often designers themselves will do glass box testing. Perhaps, for example, if you have made some changes to the code and you want to verify that things are working smoothly through each individual piece of the internals of this code, it can be quite efficient to do some glass box testing to trace through some values to make sure variables are what you expected them to be. Okay? It can be faster than guessing where bugs are. There's a crossover between glass box testing and debugging. Okay? But glass box testing is supposed to be done to verify the system, whereas debugging is supposed to be done to find where the bugs are. So anyway, I like the word glass box testing, by the way, because you're looking inside a box, whereas black box you can't see inside. A lot of people use the word white corresponding to black. I find that silly because if a box is painted white, you can't see inside it either. But people just started using the word white box for this concept. And then other people use the term structural testing. A lot of the software engineering standards talk about structural testing versus functional testing for black box testing. I don't like that distinction because, frankly, I think you're testing function and structure in this glass box testing as well. I like the term glass box, and there's a few other authors that do as well. But you might see all of them mixed up. Okay? So, in glass box testing, you will examine the design documents so that you can see places where you can put probes and where you can look at the internals of the system. You'll look at the code. You might even edit the code to put in print statements, or you'll certainly run it under a debugger, and you'll observe as the data moves through the system what's going on in detail. Okay, we're going to focus most of our attention on black box testing, because black box testing is the primary skill that you really need to learn. Practically all of you will, in your very first jobs, need to do black box testing, even if you're not a formal tester, even if you're only testing your own code. You need to know how to systematically test, and black box testing is the primary skill. Glass box testing is the secondary skill. So let's talk about how you might go about doing black box testing. One of the key strategies is to think in terms of what are called equivalence classes. Equivalence classes are groups of data that will be treated the same by the system. Okay? One thing you could do is you could do brute force testing, which means put every single possible input value into the system. So let's say I was testing a system that sorted a bunch of names. Okay, one strategy would be to put every possible combination of names of strings into the system. How long would that take? Practically forever, right? Well, it would be forever, because you can have an infinite number of possible strings, okay, assuming the length is unbounded, right? So, and I obviously can't test every possible sequence of strings to see if the system sorts it correctly. So I have to make an intelligent decision, and I have to say to myself, well, I'm going to consider many of these strings to be, or sequences of names to be behave the same way. The system will almost certainly behave the same way if I put in one set of strings as if I put in another set of strings. So what I need to do is to efficiently partition up those possible sets. So like one partition might be sets of strings which are already sorted. I'll test with those. Okay? And I will assume that most likely if I put any kind of set of strings that are already sorted into the system, hopefully the system will behave in a similar kind of way. So I don't need to all of the possible sequences of all possible strings. Another equivalence class might be all of might be a set of strings where there's a lot of duplication. So I have 5 Jim Smiths and 5 Muhammad Alis and 5 Jamie Chans, you know, and I've got 15 names with a lot of duplication. Will the system sort them correctly? Okay, that's another equivalence class because you might anticipate that the system might get confused by similar names. Okay? Now, if the system is case sensitive, okay, one of the tests I'm going to do is I'm going to make sure that I put in data where I have the same string that differs only with upper and lower case. So I put in Tim Lethbridge uppercase, Tim Lethbridge lowercase. It's a case-sensitive sort, so I expect the system to distinguish between these and sort them correctly. Okay, so I'm going to put in sequences of strings that have that quality. And I'm going to put in sequences of strings where they're all the same. I'm going to put in the empty sequence of strings. Okay? And I'm going to try all kinds of other cases where I think the system might behave differently. And each of these sets of cases where I'm trying to tease out different behavior of my algorithm is called an equivalence class. So rather than testing all possible sequences or randomly testing, I'm intelligently choosing groups of cases that I think will perhaps cause the system or might uncover bugs. Okay? So brute force testing is impractical and pointless. And the objective is to divide the possible inputs into groups that you believe will be treated similarly by algorithms. This is why, to be a tester, you need to know about programming and software design. Okay, you can't give the testing of a system to somebody who isn't a software engineer or computer scientist or doesn't have training in those areas. This has been done by people. Some managers will give people who don't have much training the testing job, thinking that, well, you don't need to know how to program a system to do testing. That's not true. To do testing, you have to have experience in programming and design because you have to be able to understand the way that designers think, the kind of algorithms they might have used, the places where they might have made mistakes. All right? Okay, so you have to look for places where algorithms will typically treat data similarly, and we call them equivalence classes. We'll see in more cases in a minute. And you only need to run one test per equivalence class to be efficient. I don't need, if I've done a good job of partitioning the system up into equivalence classes, to run a large number of tests per equivalence class. Because I've basically divided the system up into cases that I believe the system will treat all the cases in the same class the same way. All right? Here's an example. I gave you an example of sorting, but here's an example of invalid or valid month numbers. Let's imagine that I had an input into an algorithm that did something with dates, where one of the values was the valid month number from 1 to 12. What are the equivalence classes? Well, we would normally say that there are 3 equivalence classes. One equivalence class is valid data 1 to 12, in that range. Another equivalence class is values that are greater than 12, so 13 and above, and I'm using the infinity symbol here to indicate numbers which are logically the largest number that could be represented by this system. Okay? And another equivalence class is numbers that are less than the range, 0 or any number less than that, negative numbers, down to the lowest number that could be possibly input into this piece of code. Okay? So I have three equivalence classes. My data that is valid, my data that's greater than valid, my data that's less than valid. Why do I have three? Why don't I just have two equivalence classes? Valid data and invalid data. Anybody can think of why I might have the two invalid ranges of data. What's the rationale for that? Anybody can figure that one out? Yeah.
The test they did for a valid number might not be equal to 1 to 12, it might be 12 to 1.
Right, exactly. So if the system, what he's saying is that the system is likely to have an algorithm that works something like this. It's likely to say, if number greater than 12, reject it. So I got that if statement. And then I've got another one that's going to say, if value less than 1, reject it. Okay? And so I have to make sure that I'm checking that it does both of those things. If I group those two together as just invalid data as one equivalence class, and I then do one test, like the number 45, then that might be successful, and it might detect successfully whether somebody has done that greater than 12 test, but the less than 1 test is just as important, and logically, algorithmically, is a totally different kind of thing. So I've got to do equivalence. I've got to create equivalence classes that will logically consider all of the possible things that the algorithm might do incorrectly. Okay, so obviously more complicated algorithms are going to have many more equivalence classes. This is only going to have basically 2 conditions that are in there, and that's all I have to worry about is therefore these 2 invalid equivalence classes. What if I have 10 strings representing a type of fuel? Okay, type of fuel, coal, gasoline, propane, natural gas, whatever. Okay? 10 possibilities. This is a system that is dealing with computing the energy content of fuel, for example. Okay, and there's 10 possibilities it can work with. Okay, and I have to type in a string. That's the way the system works. What are the equivalence classes? Well, can I just randomly test one of those 10 values, like natural gas, to see if they type the word natural space gas? Okay, well, I obviously have to test that because I have to make sure that it will work for natural gas. I have to make sure it works for gasoline. I have to make sure it works for propane. I have to test each of those 10 cases, because the algorithm will work differently for each of those 10 cases. Okay, so if there are 10 cases where it will work differently, and there are 10 possible inputs, I have to test for those. And so each of those is its own equivalence class. And then there is also the equivalence class of all other possible strings. So I have to test to make sure that it doesn't accept gobbledygook, the word typed out, G-O-B-B-L-E, etc. I have to test, or some other string that's random. So that becomes another equivalence class. So we have 11 equivalence classes if I have 10 valid strings and everything else is invalid. Okay? Again, because in my algorithm, I'm going to be testing matches against a specific string, and I have to detect to see if there's bugs in checking that. So with numbers, I can just check ranges. With strings, I've got to check the exact value. Okay. How many people don't understand this concept? It's quite important that you get this concept. How many people do understand the concept? Good. Okay, that's great. When I have silent stares, it's often a little bit hard for me to know whether you're completely not understanding it or whether you're completely understanding it and wanting me to go on. So that's the thing. Okay, now most systems are not just receiving input from one equivalence class, one input. Most systems are not just taking a single string or a single number as input. They're taking tons and tons of inputs, all at the same time. And so to test the system, I have to, for example, if I have a fill-in form that's information about people, and I have name, phone number, postal code, age, tons of other stuff, they're all inputs independently that have to be tested. So I have to test that name is being entered properly, that phone number is being entered properly, the postal code is being entered properly, that certain sets of preferences are being correctly checked, and so on. All of those independently have to be tested, and therefore I treat each input independently. But sometimes these inputs will interact with each other. So, for example, if I said that my age was in the system was, say, less than a certain number, let's say, let's say that one of the questions was about education level, another question was about date of birth. Okay. Well, I would want to check that somebody didn't have in their system that they were 8 years old and had a university PhD degree, right? That would be invalid. And so I might have some constraints on my testing that would test combinations that would be invalid. So rather than checking that the date of birth number is valid and that the university education valid number is one of the appropriate ones that were specified, I'd want to make sure that these values make sense together. Okay? Trouble is, if I try and do that, I'm going to have a combinatorial explosion of possible combinations. I have to check every possible value that makes sense with every other possible value, and that will break down. I end up with an explosion of possible inputs. If I have 4 possible inputs with 5 possible values, I have 5 to the 4 possible system-wide equivalence classes, which are combinations of values that work with each other, if I need to check all of them. Okay? So the strategy for that is I check each individual input on its own, and then I try a subset, a selection of the combinations. I can't check all combinations because it just would be impractical. I have to make an intelligent decision about the most important combinations. In the book, there is an example that is talked about to some extent on slide 9. This example is fleshed out in more detail. I urge you to look at the book. This example is information being entered about vehicles. Okay? And one of the fields is the fuel and other properties measured in terms of the metric system, or is it measured in terms of the imperial system, or US system? And we could actually have 3 because imperial units and US units are slightly different, gallons different size, for example. But let's leave that detail aside. So, in the input where the person types metric or clicks on the metric button, clicks on the US imperial button, I have then equivalence classes, metric, US imperial, and other. If it's possible to specify some value other than these, let's say this is a typed value or a string value that comes in an input channel, I have to check to see if some other invalid value is being specified. So that's the equivalence class for this input. And then another input is maximum speed. How fast can this vehicle go? Now, this might be for cars and trucks and airplanes and boats and all kinds of vehicles. Okay? So what are the equivalence classes? Okay, if we're saying that in the metric system we're allowing speeds of 1 to 750 kilometers an hour, and in the imperial system we're allowing from 1 to 500 miles an hour. Okay, those are the values that we're allowing in our database, depending on whether metric or imperial is specified. So what equivalence classes do we have for this speed input, just considered on its own? Okay? Well, there are a number of equivalence classes. We have 1 to 500, which is common between metric and US imperial. Then there is 501 to 750, which is the values which are invalid for US imperial but are valid for metric. And then we have values that are greater than 750 and values that are less than 0, or 0 and less, which are invalid for both. Okay? So the key here is I'm splitting my valid equivalence class into 2 groups, because depending on other conditions, sometimes one range is valid, sometimes another range is valid. And I need to make sure that I do tests in both ranges, because I could have algorithmic bugs that would be only accepting, say, the US imperial range of 0 to 500, and it would reject 650 kilometers an hour. So I have to have a separate test in that higher range that's invalid for imperial but valid for metric. Okay, and so then I can do some combination testing. So for example, metric with a value in the range 1 to 500, US Imperial in the range 501 to 750. Now this is a test where I know that I expect this to be considered invalid data. And I have to check this combination, because 501 to 750 is valid for metric. Okay, so these two inputs, the type of measurement system and the number, strongly interact with each other and give rise to different results. So I have to make sure that I check these values in all their combinations. Okay, and as I said, if we have too many combinations, we have to do a subset. But in this case, I certainly would want to make sure I did all these 4 tests. In fact, the bottom test seems to be the same as the third one. I think what I meant to say was US Imperial 1 to 500 here as the final one. Okay, so I'll change that on the next iteration of the slides then for the big one. All right. So that just gives you an idea of equivalence classes and how you can appropriately combine them to make sure that you've tested all the possible things that could go wrong in algorithms. Another thing we have to do when we're testing is to test at the boundaries of equivalence classes. What I mean by this is that most bugs occur at the edges. So month numbers. We said month numbers are 1 to 12. Most bugs will occur because, for example, instead of saying rejected if it's less than 1, they say rejected if it's less than equal to 1. Or instead of saying reject if greater than 12, they say reject if greater than equal to 12. Or accept if less than 12, which means that 12 gets rejected. Okay? So what we want to test is we want to, in addition to testing some random value inside an equivalence class, we want to test, in the month number case, 0, it's 1 less than the boundary, and 1, which is 1 more than the boundary, okay? And 12 and 13. We want to make sure we test those boundary values to make sure that they haven't made mistakes with less than or greater than, less than equal, greater than equal. Very, very common bugs. The whole idea of testing is to test in situations where you expect people to make bugs. Bugs at boundaries are one of the most common kinds. So that's why we need boundary tests, as they're called. All right, so 0 is a particularly common problem in systems which should accept greater than 0 and not 0, for example. Any questions? Okay, so boundary testing is detecting a particular category of defects. It's detecting these defects that are caused by inappropriate less than or greater than symbols. There are many, many other categories of defects that we also want to try and detect, and we're going to talk about those now. First of all, I'm going to talk about defects in ordinary algorithms. Okay, defects in ordinary algorithms. There's a number of particular kinds of defects that are common, and we're going to just go through those. And then I'll talk about numerical algorithms, and then stress tests, and a few other kinds of tests. The idea behind these sections is to open your eyes to things that when you're testing, you need to check for. Some of them are obvious, others will be less obvious. But it'll give you a catalog of things to watch out for, things to design tests for. So first of all, incorrect logical conditions. So the less than greater than thing is a logical condition problem. But there are other logical conditions that are much, much more complicated than that. There's some examples in the book for all of these, and the slides are going into these in less detail, but sometimes you have conditions that say if x is greater than 7 and y is less than 10, or b is greater than 978, okay? To start with, we shouldn't hard code numbers like 978 and 10, but assume that that's the condition that works out. Okay, that's a complex condition, and we have to check for all the possible bugs in all the possible aspects of that condition, and make sure that all the possible cases, we can draw a Venn diagram, make sure all the possible cases are appropriately tested for. Okay? Here, for example, isn't exactly that. This is a statement from a piece of requirements for deciding whether some landing gear in a plane should be lowered or not. The concept is that the landing gear should be lowered when the plane is going to land or might need to land in an emergency. So we say, well, if the plane is within a certain amount of time of landing on the ground or within a certain distance from the ground, the landing gear should be down, whether or not we're taking off or landing. Because if we're taking off, that's a dangerous time. We might have to do an emergency landing. So we should keep the landing gear down for a little while and only raise it once we've got to a certain altitude after a certain amount of time. Okay? So this is for some arbitrary plane that might be reasonable. It says here the landing gear must be deployed whenever a plane is within 2 minutes from landing or takeoff, or within 2,000 feet from the ground. They typically still measure altitude in feet in many cases. If visibility is less than 1,000 feet, however, okay, so if visibility is restricted, then we're going to have more stringent requirements. The landing gear must be deployed whenever the plane is within 3 minutes from landing, or lower than 2,500 feet. Okay, so we raise the altitude requirements and increase the time requirements because we're in a more dangerous situation. Okay, the pilots might be more easily distracted, more likely to forget to put the landing gear down, or might miscalculate the altitude more easily, things like that. Okay? So that gives rise to a very, very complicated condition here. And because the requirements have this condition, the condition is going to have to be embedded in the code. So what we're going to have to do is we're going to have to do our testing to make sure that all of these all possible combinations of valid and invalid values are taken account of in our testing. And what I've done here is I've shown a Venn diagram on the bottom right of slide 13, where I have various regions where different combinations of conditions are true. So, for example, the top ellipse is visibility less than 1,000 feet. Everything outside of that is visibility greater than or equal to 1,000 feet. Okay? And so regions B, D, E, and a number of others, smaller regions that are further inside, are all regions in which visibility less than 1,000 feet is true, and intersecting with other regions where other things are also true. So to do a thorough job of testing, in a safety critical system like this, I have to test values that are in each of these intersecting ranges. So for example, area A is 2 to 3 minutes after or prior to takeoff, within that 2 to 3 minute range. Area D is the intersection of this 2 to 3 minutes after or prior to takeoff and visibility less than 1,000 feet. So I want to do a test which has both of those things true at the same time. All right? And right in the middle, there's a number of possible things. The very center is on the ground. Okay, well, hopefully my landing gear is extended when I'm on the ground. It's hard to get on the ground if it's not. You know, it's hard to retract it if I'm on the ground. You know, you have to be in the air to retract it. So that's a case that is, you know, logically right in the center where a whole bunch of things are true, and we have to test for those cases. There is a bug in this code. Okay, the Venn diagram shows all the cases, but the code has a bug, and one of the typical situations that you find in code like this is that people misplace the parentheses. So, and misgroup the ands and the ors. And so in this code, and I'm not going to go and spend my time digging through it now, I'll let you look at this yourself, but there is a bug in this that focuses on the fact that I haven't grouped these things together appropriately. And so I'm doing, I'm mixing up my ands and my ors in some way. I'll let you take a look at that and figure that out for yourself as an exercise. Very, very common to see that kind of bug, though. And that's why we have to test all these cases. A program could stare at this and think it's correct forever. Because sometimes when you've coded something, you're just blind to the defect. And that's why the testing is so critical in these circumstances. By the way, it's also possible to do a mathematical analysis of conditional statements. And so there are various formal techniques you can use as well to test for these things. But to prove that the statement is correct. But you should also test anyway, because sometimes the proof systems go wrong as well. Any questions about this? Okay, let's talk about calculating in the wrong part of a control construct. Okay, sometimes what you want to do is you want to increment a counter every time around a loop. But the bug is that that counter is incremented before the loop starts or after the loop ends. Or both. Maybe it's incremented in the loop every time and again after the loop ends. Okay? So all of these are cases where we're going to end up, after this is executed, with a value that is either equal to 1, because it was only incremented once, or equal to the number of times through the loop, or equal to 1 more than the number of times through the loop. And only one of those is valid. So we have to make sure that we know, based on the requirements, which value should be valid, and logically test to make sure that our numbers have been incremented an appropriate number of times. So typically, is the system capable of counting correctly? That's what we want to test here. And we'll often find that there are bugs where this is not done, where the system is off by 1. It counts 1 too few times, 1 too many times. That's a very, very common style of bug. So whenever you have in your requirements something which is going to be done repetitively, make sure that it gets the number of times through correct. Exactly. Not approximately. Exactly. Because otherwise you will run into bugs. You want to design tests that execute each loop 0 times, because sometimes 1 is the default. But if there's 0 entities, let's say you're counting number of students in a class. Well, if there's no students registered, you want the result to be 0. You don't want the result to be 1. What you might have is an initialization, initial the value to 1, and then add 1 every time. Well, then you get too many, right? You want to make sure that 0 really comes out as 0. Okay? And you want to make sure that you test for situations where strange things happen in the first iteration through the loop and in the last iteration through the loop, to make sure that the loop counters are properly being dealt with on all of these iterations. Okay? So you're not actually seeing the code. What you're doing is you're looking at the requirements, looking for things where things are done repetitively, and making sure that the system behaves appropriately in all extremes of repetition. Okay? So here's a classic example. Okay? While j less than maximum, assign to k the value of some operation on j, and then increment j. Okay? If k equals -1, signal an error. Okay? Now the problem here is that if this thing loops only 0 times, right, which it might, if j is greater than maximum or equal to maximum to start with, k is never going to be set. So k might be set to some invalid value that was, initialized earlier, or maybe in a previous iteration of this loop, and we get an inappropriate result because we didn't think about the 0 case. So always check for 0 iterations. Okay? Not terminating loops is another typical classic problem in software engineering. There needs to be always situations where loops will terminate. Our job is to see if we can get the system to go into an infinite loop. Can we cook up, can we invent, can we imagine a way in which we can force a system into an infinite loop? Your job is to try to crash the system as a tester. Okay? In each case is different. See if you can figure out a way of doing that. Maybe by supplying data which in some kind of data structure which goes around in a loop. Okay, so let's say the system was expecting to work on object 1, object 2, object 3, when they point to each other. But what you do is you make object 3 point back to object 1. Now, is the system smart enough to not go around 1, 2, 3 and then back 1, 2, 3, 1, 2, 3, 1, 2, 3 forever? Okay? See if you can come up with a construct or a type of input that would cause a system to loop infinitely. See if the system is smart enough to figure out that it shouldn't do it, loop infinitely. Okay? And not setting up the correct preconditions. We talked about preconditions briefly the other day. Precondition is something that must be true before an algorithm executes. And our job is to see if we can get the system to accept inputs without these preconditions being set correctly. Okay? So if a precondition is that you must be registered in the course before you can take the exam, we'll see if the system will let somebody take an exam even if they're not registered in the course. That's an example of testing to see if the preconditions have been set. Not handling null conditions is another one. We want to check to see if the system can handle data which doesn't point anywhere or is zero. Okay? Normally we have one or more items to process. We're going to try to see what happens if there is nothing. What if there are no students in the course? Is the system still going to schedule the exam? Okay? We want to find that out. It turns out the University of Ottawa, when it's scheduling exams, it figures the rooms based on the number of people originally registered, and doesn't, even the people who dropped are still scheduled for an exam. So if everybody drops out of the course, the system will still schedule an exam for the course, which is dumb, but that's the way the system, at least up until this year, I don't know if they fixed it yet, it actually still works. Okay, so last year I was able to get my class put into a better room because I pointed out that we had 10 people drop, and it had forced me into a larger room, and I said we can go into a smaller room, much nicer. And I had to prove to them that in fact these people had dropped even though it was in their database. Okay? So that wasn't a null condition, but in the logical extension of that, if everybody dropped, it would still have to be an exam in the course. Okay? So we have to watch out for that. The way you test for this is you have to systematically analyze the requirements to see if there are any null conditions. Think brainstorm. What kinds of null conditions are there out there that we have to test for? All right? So we'll pick up from here on next class, and we'll get most of the way through testing, and we've got 2 more lectures to go, so we should be able to get through most of this.